Okay, our final lesson in Unit 6 is dealing with solving these exponential equations and logarithmic equations, understanding the inverse relationship, and applying along with properties of logarithms to be able to solve these equations. So our goal is to make sure that we can work with that inverse relationship, apply those properties for logarithms to make single logs or make single exponential expressions, and then perform these inverse operations. This does require that we did well with lesson 3 and that we did well with lesson 5. Mostly lesson 3 though, and then some of our lesson 5 work will be towards the harder examples at the end. One of the things that you'll notice is that our calculators have the natural log button and they have the common log button, log base 10. And so the question is, how do we evaluate logs when we don't know, not when we don't know, but when the base is different than e or 10? Well, this is our change of base formula, which basically says log base b of a number is found by taking log base 10 of the number divided by log base 10 of the base. You can also use natural log. All right, you can also use natural log if you would like to. My work is going to be focused on just using log base 10. That's what our examples are going to look like here in our notes. But you can use, really, any base, all right, to modify that relationship. And here's where you're actually doing operations with logarithms that is different from what we did with like the quotient property. So for example, this I could write as log base 10 of 12 over log base 10 of 6. All right, I can write this one as log base 10 of 13 over log base 10 of 18. I can then evaluate that expression, all right? And so what that means is I can write log of 12 and divide it by log of 6. We are going to approximate that, and it's going to equal 1.3869. We're going to go 4 decimal places. When I type log of 13, close parentheses, divided by log of 18, close parentheses, it's going to give me approximately 0.8874. And so here's what that looks like in the calculator, all right? Log base 10 of 12 divided by log base 10 of 6, log base 10 of 13 divided by log base 10 of 18. And then we've approximated those to 4 decimal places. Sorry for the typo in the directions here. To evaluate the expression. That's what that should say. So sorry, that's why I was having like an aneurysm looking at that. I was like, oh my gosh, I can't read what that says. All right, and then now we're going to use logarithms to write the equations, these exponential equations in logarithmic form, and then of course be able to solve for the variable. So for example, I could just take the common log base 10 on both sides. If I take log base 10 on both sides, then what that is going to give me is it's going to give me this situation where I can now use the power property to bring that exponent down. If I want to get x by itself, I can divide by 2 and I can divide by the log of 5. So if I divide both sides by 2 log 5, I would have this equation, and that would let me approximate x. Now there's another way that we can do this, and I want to talk about why that change of base conversation was part of the example there. But another thing that I want to reference is how we type this in our calculators. All right, so this gives me 1.4873, all right, 1.4873. But look at how I have to type this. I'm going to do the log of 120 and close my parentheses. And then in my denominator, I have a product. I've got 2 times the log of 5. And so I've got to close the parentheses around that log of 5, and then I need to close the parentheses around the denominator 2 times the log of 5 to get my 1.4873, all right? 1.4873. Now, here what I did is I performed inverse operations by taking log base 10 on both sides. But if we are using the inverse relationship between exponentiation and logarithms, then I would understand that 2x is equal to log base 5 of 120. And so x would be half of log base 5 of 120. Or log base 5 of 120 divided by 2. All right, so same idea. The problem is that our calculators, again, we're not able to change the logs in most of these calculators, or the base of the logs in most of these calculators. So that means that I would have half of, then do the change of base, the log base 10 of 120 log base 10 of the base. All right, which gives me the same situation, the log of 120 over 2 times the log of 5. All right, so it ends up looking the same, but maybe undergoing different operations. Obviously, either way you do that is totally fine by me. We are going to subtract 4 first from both sides to get 2996. And then we are going to, let's do this form right here. We're going to write the exponent is equal to the log of the base of our power of this value, which means that we have 5x is equal to this thing minus 1, and x will equal 1/5 times log base 7 of 2996 minus 1. All right, now for this part, we might need to write that, and maybe even earlier in our work, we might need to write that as log of 2996 over 7, all right, and then minus 1. We don't want to have a fraction in our fraction, so that's why I'm kind of leaving that the way it is. If you want to distribute that 1/5 in there, you're welcome to, but again, we want to be able to approximate that. So I'm going to take 1 divided by 5, and I'm going to multiply that by the log of 2996, close parentheses, divided by, whoops, the log of 7. Come on, Mr. Hibbett. Divided by the log of 7. Did you catch that mistake or no? By the log of 7. And then I'm going to subtract 1 and then close my parentheses. So, whoops. Let's go to, let's find where my mistake is. And we get 0.62275. So I'm going to call that 8. So that is our approximated value. Again, if we wanted to subtract the 4 first and then take the common log on both sides, we wouldn't have to go from this to that. We would just make it that, kind of at the offset. And that was just kind of be how you could approach that. I'm a big fan of just taking the logarithm on both sides. I'm actually a bigger fan of just taking the natural log on both sides, but again, we'll check through that as much as we need to. All right, so here are these ones. We're going to divide first by 4. All right, and the reason why we're doing that is we're getting the exponent part by itself. If we have the base to the power, great. If we have things being added or multiplied, then it's not by itself yet, and it'll make our lives easier if we are able to just write this in the exponential form, so that we can write it in logarithmic form, and then we can solve. This is the exact value for x, the natural log of 8 minus 2, but we're going to approximate that. So again, that's the natural log of 8, close parentheses, and then minus 2 separate from that, 0.0794. All right? I want for you to try, well, I'll just do it, I don't care. We're going to take the log base 10 on both sides, and that's going to just give us our exponent. So the log of 25 plus 1 is equal to x. Again, it's the log of 25. All right? Close parentheses, and then add 1. Just like this was the natural log of 8, and then minus 2. So this gives us 2.3979 is approximately equal to x. All right, so the weird thing about these equations is that you have no sense of whether or not those answers are correct, right? And so it becomes a little bit problematic, but since we are rounding these values, we know that this is not exact. But I could take 10 to the power, and in that power, I could make sure if I need to put parentheses, I could, but 2.3979, all right, minus 1. And does that give me about 25? Oh man, I need it as a decimal. This is calculator. Come on, dude. Let's change that answer. Again, math, we're going to change it to a decimal. Boop. And it gives me almost 25. Okay, so I'm using an approximated value, so I'm not getting quite 25, but we know that our answer is about correct. We've approximated about a correct answer. All right, moving on. Here we are still solving these exponential equations. I want for you to try both of these just for the interest of time. I'll tell you what to do, so if you listen, you'll know what to do. You're going to subtract the constant from both sides. On this one, you're going to take the natural log of both sides. It's going to give you the exponent is the natural log of that difference. Multiply by 5, divide by 2. Over here, after you've subtracted, you're going to divide by 7. Get this factor out of there. Divide both sides by 7. Then take the natural log. So you have 2x equals that difference divided by 7. and then you can, and then you will be able to solve that equation. All right, divide by, and go from there. So you try those two, and then we'll go from there. All right, now solving logarithmic equations, because I don't want this to go any longer than it's already going. We're already at 10 minutes. I've got a handful more of these to do. So I want to give you lots of examples. I want to give you opportunities to practice, but then at the same time, I want to make sure that you see some good examples. Remember, this is base 10, right? This is base 10. So if I write this in exponential form, I have this situation. Now, 10 to the fourth, we could evaluate that, or we could recognize that we're going to take whatever 10 to the fourth is, and we're going to be adding 2, and then we're going to be dividing by 2. 10 to the fourth plus 2, and then divide everything by 2. We need parentheses there or whatever else. I'm kind of a fan of taking 10 to the fourth and actually finding out what it is, so that this math looks a little bit easier. We'd have 2x minus 2 is equal to 10,000, which means that 2x is equal to 10,002, which means that x would be that 10,002, but then divided by 2 to get 5,000. I don't know why I used a calculator on that. And we get what x is equal to exactly, 5,001. Here we're going to want to add 7 first. And then we're going to say x is 10 to the 6th power, all right, which is a million. All right, so we want to make sure that we can follow those orders, those steps, do our orders of operations in reverse when we are solving equations. We do PEMDAS backwards when solving. We got to get the log by itself. Once the log is by itself, we should be good to go. Go ahead and try these before I get there. See how you do. See if you can do those steps. We divided both sides by -2 to get a positive 7. We took 3 to the 7th power is equal to x squared. I don't care what 3 to the 7th power is. We're going to take the square root of 3 to the 7th power. If you wanted to write that as the square root of 3 to the 7th, or if you wanted to write that as the square root of 2187, and then simplify that radical, that would be fine with me. But there is your decimal approximation. All right, I'm okay with decimal approximations. Let's go ahead and try letter D here. This is going to equal that. You solve. Solve that, all right? So we write it from logarithmic form into exponential form, and then we do our PEMDAS in reverse to get the variable by itself. Let's see if you can do that one. All right. For these, obviously we want to try to break this down as many ways as possible. I would love for you to do some solving on this, so have that calculator handy. But let's do these. We're going to have x plus 2 over 3 is equal to e to the 12th, which means that x plus 2 is going to equal 3e to the 12th, and x is going to equal 3e to the 12th minus 2. Type that in your calculator to approximate. Over here, this argument is going to equal the base to the power 4, which is 16. We can solve that equation probably without a calculator to find out what x equals. And then we can check our answer to tell me if I made a horrible error in that work. All right, now using the properties. This is really the punchline to all that work. So hopefully you're able to solve those things. You're able to do that work using exponentiation or logarithms. Here, we're going to have to use those properties of logarithms to recognize that I have the log of 6 over 3x is equal to -2, which what this means for us is that we have the log of 2 over x is equal to -2, and so 2 over x is equal to 10 to the -2nd power, or 2 over x is equal to 1/100th, which means that 200, if I cross multiply, is equal to x. Over here, let's try to combine these. This is the log of x cubed minus the log of 2 equals 5, which means I have the log of x cubed over 2 is equal to 5. And so that means x cubed over 2 is equal to 10 to the 5th. And so x cubed over 2 is equal to 100,000. x cubed is equal to 200,000. And then x is going to be the cube root of 200,000, which is approximately equal to, and then you can type that in your calculator, what that is approximately equal to. Okay, so let's see how those go for us. Can we use these properties to solve these scenarios? All right, to solve these equations. In this case, we are going to combine these natural logs as x plus 2 over 4, and then we're going to write it in exponential form. All right, writing it as a single logarithm to then write it in exponential form. Now from here, it's cake, right? We're going to multiply both sides by 4, and then we're going to subtract 2. And then we can approximate that. We know what x equals. Do we know what x is approximately equal to? I want for you to do letter D. And then we'll see how that goes. There's one more example here, but I'd like to do it in class, and I would love for us to take this and make sure that we feel good for our very last set of notes.